Welcome to lecture 6 of design and analysis of algorithms. Here we're going to discuss about solving recurrences using back substitution method. Using back substitution method, we can solve recurrences. It is a very useful method for solving recurrences or recursive equations. Now, what are those recurrences? Recurrence refers to a recursive a relationship where a problem is broken down into smaller subproblems and then those subproblems are solved independently and then again combined to solve the original problem. Now, for example, here the question is to solve the following recurrences using the back substitution method. Let's say this is the question 1. This question we need to solve using back substitution method. So here we will understand what is the meaning of recurrence and how we can use back substitution method to solve this kind of recurrences. Now here you see Tn is equal to 2t n by 2 plus n if n is not equal to 1. If n is equal to 1, then this is the base case, then Tn is equal to 1. Now, this kind of recurrence you will see in divide and conquer approach that we will discuss later. But for the time being, now here a problem of size n is broken down into two sub problems. Here you see 2 is there. A problem of size n is broken down into two sub problems. Each of the sub problem is having size n by 2. So here it is also n by 2. Now what is n here? N is the cost of dividing and combining together. What do I mean by that? The problem size n is broken into two sub problems here. As you can see here, each of the sub problem is having n by 2 size. Now we will solve independently these smaller sub problems and then we will combine to get or to provide the solution for the problem of size n. Okay. So basically you will see this kind of recurrences in recursive algorithms obviously. So we will discuss how to find out time complexity of recursive algorithms in the upcoming lectures. There we will see how we can get this kind of recurrences. Now for the time being, let's understand that this recurrence is given. You need to solve the recurrence to provide the solution for Tn using back substitution method. That is what we are going to discuss here. Now I will write here Tn equal 2t n by 2 plus n. So now I will back substitute t n by 2. So here you see when the problem size was n, the expression was 2t n by 2 plus n. Now the problem size becomes what? N by 2. So what it will be? 2t n by 2 by 2. So it is what? N by 2 square. So I will not write 4 here because I am in search of a pattern. I want to find out a pattern. So I need to at least expand up to 2 or 3 terms. Okay. So then if I get a pattern, then I will write a generic term for that. So 2t n by 2 square plus n. But here our n is what? N by 2. So here it will be n by 2 plus this n was there. So as it is, I have written n. So if I evaluate it, what I will get? 2 square t n by 2 square plus it will be n, 2 into n by 2, it will be n plus n twice n. So if I further back substitute for t n by 2 square, then what I will get? So surely I will get what? 2 cube t you can write down and then you can evaluate like as we have seen here. So t, it will be Tn by 2q plus here it will be 3n. Okay. Now, if I expand like this, okay, if I write like this, so if I want to write a generic term, so let's say I do not know where it is going to stop because this recurrence has to stop somewhere. But I know that here it is given, it will stop if n equal to 1, then it will reach the base condition. That is what Tn equal to 1. Means what? Here it should be 1. Then only it will be T1 equal to 1. So now here you see, I will write in, say it is going up to k. Okay. So then 2 to the power k, T n by 2 to the power k. K we do not know. Okay. So we will find out what is it. Okay. So plus what it will be? 2 to the power k T n by 2 to the power k. Here you see 3, 3. Here also 3. Here it will be what? K into n. Okay. Now it has to stop somewhere, right? So to stop, what we will put here instead of n by 2 to the power k, we should get what? We should get here 1. If it will be 1, then T1 equal to 1. That will be the base condition, right? So let's say here put n by 2 to the power k is equal to 1 because we need to meet the base criteria. Okay. So now here what we do not know? We do not know k. Okay. So I can write 2 to the power k is equal to n. Now if we go with the definition of logarithm, what I can write? How to find out k? K will be equal to log n base 2. So this is k. So now here now we know k. So just in place of k you write down. So 2 to the power what? K is log n base 2. So here I can write log n base 2. So here it is T n by 2 to the power k. We just here we can put 1. So T1 plus k is what? Log n base 2. So here I can write what? N, this n here. Log n base 2. Okay. So now I'm writing here. So here you see there is an interesting formula in logarithm. So if you do not know, just revise it. So the thing is that if I write a to the power log x base b, this we can write, we can interchange these two, a and x. Okay. So here if we interchange, we will get x to the power log a base b. Very important formula. So here you see 2 to the power log n base 2. So here it is in terms of n. The power is in terms of n. So can we do something here to evaluate it? Okay, we will interchange this 2 and n. Okay, so it will be what? N to the power log 2 base 2, and you know that log 2 base 2, that is 1, right? So and T1, what is T1? T1 means this n is 1, right? So T1 when n equal to 1, Tn equal to 1 means T1 equal to 1. So here instead of writing T1, I will write 1 plus n log n base 2. Okay. So this whole thing becomes what? This is equal to this whole thing. This is equal to this n to the power 1 because log 2 base 2. So n plus n log n base 2. So it is nothing but n plus n log n. Now if I write using asymptotic notation like big O, so there I only care about the highest order term or the asymptotic growth rate, whichever term is having higher growth rate that I will write. Other things will be dominated by the highest order term when we think of some large value of n. So we have seen these things in the earlier video lectures. So if you have not seen those, please watch those videos to clear your concepts about asymptotic notation. So here the highest order term between this n and n log n is nothing but what? N log n. So I can write n log n. So this is our solution. In the question it was uh, asked that solve the following recurrences using back substitution method. So this was the solution up to here, and then we expressed the solution using big O. Now here you see, here I have written one thing, like when you will see log n base 2, and in algorithm you will see almost in all the places we only care about base 2. So this whole thing can be written as LGN. Okay, so here just I have written that it looks very clear in that sense. Otherwise you can write okay log n base 2 also. Okay, so this is the solution. This is how we solve using substitution method. Okay, next example we will see. Now here you see, here the example, here also the input size is getting reduced, but not by division, by subtraction. Okay, so this we can term as subtract and conquer or decrease and conquer. We will see this kind of thing in the upcoming lectures. So here you will see how to solve it. Okay, so Tn is equal to 2T n minus 1 plus 1, right? So here you can see that n, when n will be equal to 0, then t n equal to 1, means for the base condition is for n equal to 0, because it is the input size is getting reduced by subtraction. Okay, in case of division, in most of the cases you will see that when n will be equal to 1, then it will reach the base condition. Okay, whatever. So now you see, again similarly as we have seen earlier, so here we will, instead of writing t n minus 1, we will back substitute something equivalent to that thing, okay, in terms of recursion. Okay, so if Tn equal to 2T n minus 1 plus 1, so what will be T n minus 1? So here our n is n minus 1, right? So here the 2 as it is, then T n minus 1, it will be what? 2 T n minus 2 plus this one, and then as it is, this one, right? So 2 square, if I evaluate, 2 square T n minus 2 plus, it will be 2 plus 1, 2 into 1, here it will be 2, 2 plus 1, here it will be 3, right? So next, I mean, if I back substitute, so it will be 2 square T n minus 2, so here it will be 2 T n minus 3 plus 1 plus this 3, right? This 3. So if I evaluate, so here what I will get? So 2 cube, here I will get 2 cube T n minus 3 plus 2 square into 1, 4, 4 plus 3, 7. Can you see a pattern here? So here you see, so let's say we are assuming that it will stop somewhere at k. We do not know k, we will find out. Okay, so 2 to the power k, here it will be T n minus k. Here you can see, so if you think this 3, here also it is 3. So let's say it is going to stop at k. Now n minus k plus, here you see at this point we got 1. Okay, and then we got 3, and then we got here 7. So what can we think about in terms of this generic term k? So if you see here, you see this one, it is 2 to the power 1 minus 1, right? Just observe here. So 3 is what? 2 square minus 1. Why I am matching in that way? Because here you see it is 2, here also I will get 2. Here it is 1, here also I will get 1. So in place of this 7, what can we write? 2q minus 1, right? So if I can do that, so here generic term what I can write? 2 to the power k minus 1. Yes. Now here you see, so in place of n minus k we should get 0. Then only we will reach the base condition, because here it is given n equal to 0. When n equal to 0, Tn will be equal to 1, right? So okay, put n minus k equal to 0. So what we do not know here? We do not know k. So k will be equal to n. So after that, again you come here and then write 2 to the power k. So in place of k, you will write n. So now this time Tn minus k. So n minus k we know, we put n minus k equal to 0. So it will be T0 plus 2 to the power, what is k? K is n minus 1. So this whole thing can be written, here I am writing. So 2 to the power n, so what is T0? T0 is our base condition. When n equal to 0, it will be T0, that is 1, right? So 2 to the power n multiplied with 1, right? Plus 2 to the power n minus 1. So now you see, so here if I express in terms of asymptotic notation, so then I will only care about the highest order term, so that is 2 to the power n. A third example here, now we will solve quickly because we know how to proceed. So Tn equal to T n minus 1 plus, this time it is log n. Okay, so if I substitute, what I will get? So in place of Tn minus 1, what I can write? I can write Tn minus 2 plus log what? N minus 1. Why? Because when it was n, Tn is equal to Tn minus 1 plus log n. Now our n is what? N minus 1. So Tn minus 1 equal to Tn minus 2 plus log n minus 1. Now you just write this log n here. Okay, fine. Okay, so what we can write? So Tn minus 2 plus, here you see, for simplicity we will not write log n minus 1, log n minus 2 like that, because asymptotically we are going to provide the solution here. So in place of log n minus 1, I will directly write log. So if I directly write in place of this log n minus 1, so if I directly write log n, okay, approximating in that way. I mean, we are going to provide the solution in terms of asymptotic notation like Vigo. Okay. Okay. So here log n plus log n, it is what? 2 into log n. So 2 log n. So n minus 3 here it will be, and here it will be what? 3 log n. Okay. So this way it will go. Let's say we are going to stop at k. So T n minus k plus k log n. Okay, so we do not know k, so we will find it out. But here to reach the base condition n minus k, we need to put n minus k is equal to 0, because then only we will reach the base condition. Now what we do not know? K we do not know, so k will be equal to n. So here again you come, so in place of T n minus k, what we will write? T0 plus, what is k? K is n. So n log n. Okay. So now what is T0? T0 is nothing but 1, base condition, right? So 1 plus n log n. So if I write using Vigo upper bound, so I will only write the highest order term and I will neglect the lower order terms and constants. Okay, so n log n. So here the base is 2, right? So you can either write n log n or base 2, or you can write what? N LG n. We have seen earlier that if the base is 2, then we can write like that. Okay. So this is the solution here. Okay. So now the next one. Now here in this problem, so we will write what? Tn equal to t. So here you see, here it is given t eighth root, okay, n. So what I am going to write? So I can write n to the power 1 by a plus 1. So I am writing in this way to clearly observe some pattern. Okay. So now if Tn is equal to T n to the power 1 by a plus 1, then what we can write in place of T n to the power 1 by a. Okay. So if we substitute, then we can write what? T n to the power 1 by a. This is now our n. N to the power 1 by a is now our n. Right. So it will be n to the power 1 by a to the power 1 by a. So it is n to the power 1 by a square, right, plus 1. Okay. So this is for this substitution. Okay, plus this one as it is, this one. So here if I write, so t n to the power, keep it like that only, s squared, plus here it is what, 1 plus 1, 2. So it will be what? T n to the power 1 by a cube. Similarly you can write as we have seen here. Okay. So plus there it will be 3. We will find 3. Okay. So here a and b are, you can assume constants in that way. Okay. So let's say up to k it will go. So t n to the power 1 by a to the power k plus k. Okay. In general, we can write this way because here you see 3, here also 3. So if we assume that okay, it's going to stop at k, so here in place of 3 we'll write k. Okay, no problem. So here you put n to the power 1 by a to the power k. This whole thing should be equal to what? Here you see very carefully. When n equal to b, then we will reach the base condition. Okay, so n should be equal to b. Means here we need to get b. So means whole thing will assume this is equal to b. So here we do not know k, right? So we need to find it out. Okay. So how we will find it out? So n to the power something. So if I am going to calculate this power, so I can think about logarithm. Okay. So here by definition of logarithm, 1 by a to the power k will be equal to what? Log b base n. Okay. Now there is another property of logarithm. If I write a to the power k, so this base will change. Yes. Log n base b. It will be there. Now again I need to find out k because we do not know k. So here k is what? Again logarithm. Log, then this log n base b. What will be the base here? A. Right? So this is our k now. Okay. So t in place of n to the power 1 by a to the power k, we will write b. So plus k. So in place of k, what we will write? Log n. Here the base is b. Here it is a. Now what is tb? This is the base condition. That is 1. Okay. So in place of that, we will write 1. So 1 plus log, here also log n B, here the base is A. So if I write asymptotically, to provide the upper bound, so I can only write this term. So it will be log n, here the base is B, here is A. So this is our solution. So this is the way how we can solve recurrences using back substitution method. The important thing is that you will substitute the term, okay, like here we have seen that t n to the power 1 by a, so we have substituted, okay. So and then we will observe a pattern. So if we can find a pattern, we will write in terms of k, that we will assume that okay, at some k it will stop. Now what is the stopping criteria? We need to reach the base condition. Now this kind of base condition will be given, okay. So then you will try to meet the base condition, and then accordingly you will find the unknown parameter, like here it is k. So then you will substitute that thing and you will get the answer in terms of asymptotic notation. Now, if you want to find the answer up to here, if you do not want to provide the asymptotic notation in terms of asymptotic notation, you can keep here also. But if in the question it is given, if it is given that okay, you provide the upper bound, then you can show in that way. Okay, so these are the 4 examples we have seen how to solve recurrences using back substitution method. We will discuss in the upcoming lectures other methods of solving this kind of recurrence. Thank you.